Okay, so now here's the question. How to reduce the energy cost of convenience? And so one way to look at that is shown here, is we want to lower the slope of the line. So we want to take ourselves by materials development from our original plot to somehow attaining a slope which is where the green line is. So if we can reduce the energy cost of the convenience provided by whatever the service is, and end up at the green line, we'd be heading towards an objective which is totally consistent with a more circular economy, but more broadly defined here. Okay, so let's look at now. I think I've only got three or four strategies for you on how we can do this, and they're fairly obvious, but just bear with me and we can work through them and how it relates to a material. So the first one, which you're already thinking, is to repurpose, to reuse and recycle. And that actually leads to an energy cost, and I'll show you the little diagram how. And so that what we're trying to do here is to maximize the circularity credit. So the way to analyze this, so here we've got we've gone to the green line, which is the slope we wanted, with our same component. In this case, the lifetime is kept the same, but we now consider that there's an energy to create a new product, of course, but then there's a circularity credit. So what we do with the old product provides a credit for energy. So that old product is going to put energy back into the system in one way or another. The crudest way, of course, is to burn the product and extract the energy and turn it to electricity. That is the crudest. That is the ultimate in downcycling, if you like. And there's other ways, of course, that we could consider how to maximize the use of the energy that we've already invested in that product. And the way to account for it is shown here, that it's an energy that you return, and then the net result is a lowered energy of convenience. Okay, so that's one that comes to mind straight away with a circular economy. And by separating it into these two aspects of the loop, it can inform what we do with a material or with a product. And so for one example, and this is an example that was developed a few years ago by the Agency of Design in the UK, is to create a product that is very easy to disassemble for material recovery. So this product it's full of fixtures that are very easily released. And what they do is they just put this prototype toaster, they put it in a little space, and then they lower the pressure of the space just slightly. And all these components then pop apart, and basically the toaster disassembles itself just with a reduction in pressure. I mean, it's just an example, but it shows that how the thinking can lead to a product design. And in this case, the product is one that disassembles itself. Now we're interested in the material level, and so the material and what are the material solutions that we can come up with to facilitate this sort of thing. So that's one example of how we might design products and materials to facilitate a lower energy cost of the convenience of being able to toast. Okay, here's another one. So this is fairly straightforward, just simply reduce the energy of replacement. So maybe we refurbish it, or we develop new technologies to manufacture. This now is a separate strategy than the circularity credit, but it just shows that, and this is an ongoing thing. How can we make steel with less energy? This leads into this very same objective of attaining a lower slope of our green line, lowering the energy of replacement. Another one is to improve the ability to repair and its repairability. And see, in this case, we actually don't change the energy of replacement, but we just make it last longer. But it feeds into exactly the same graph, and it's another strategy to achieving our desired reduction in the slope of our energy cost line. So improving repairability. Now, how can we do that for materials? Lots of different ways we can do it with materials. But let's just go back to our little toaster. And this is the case where you might design something that is pragmatic. So it's a modular product. And so bits are easily removed and easily repaired in this case. And it's certainly at the material level, we can make materials that more readily lend themselves to welding, for instance, or rejoining or refurbishing, or even there's self-healing classes of materials that fall under this category of being able to make things more readily repaired. So I know this is fairly straightforward, but still still think it's an interesting way that helps us consider when we've got a materials development problem on our hands, how to attack it. Okay. Now, increased durability for longer life. And so this is fairly straightforward again. How can we develop materials that last much longer before they need to be repaired? And in the first instance, someone might not think, oh, well, that's not making a circular material. But it's probably better to make a material that lasts longer than to make a material that's easily recycled, because we still head towards this lowered energy cost of convenience. All right, well, there's some ways of thinking about it, and then how we implement them in the toaster in this case is to make a toaster that's pretty much bulletproof. And this was a prototype that the Agency of Design came up with as well. It might not be the prettiest product to have in your kitchen, but certainly it has the appearance that you could drive over it with a truck and it would survive quite nicely. Thank you very much. All right, so how do we implement some of this in materials? Just got a couple of quick examples, and then I'll be done. So one approach is to repurpose metal without remelting. That saves a whole lot of energy because melting costs an extra amount of energy. And so we're kind of inspired by this UN statute. And there's a technology that we're working on called additive friction stir deposition. It's a bit of a mouthful, but the idea is we can take scrap metal and then we can 3D print it into large components. Here's just some examples, snapshots here. So large components that we can make from recycled metal chips without remelting them, saving the energy. Another thing that we're working on, we've had a centre that's focused on extending the life of components in mining, for instance. So wear life extension in mining is one, and then also looking at metal products that are modular in design, so they can be more easily reused. So fitting into these strategies that we considered. So they're just three little examples of things that we're attacking in the alloy space, and that's me. So engaging with the circular economy, I'd like to propose is to engage with lowering the energy and, of course, the associated emissions of convenience. So I'm done, Mayuri.
Thanks, Matt. I like your new definition, having the same convenience with low energy and finding ways to do it. And the toaster, which is more like armor, is quite interesting too. So I'll hand over to Ali, I guess, and then we could go for the question session at the end.
Thank you, Mayuri. Good afternoon, everyone. Good morning, Matt. Good morning to all of you who are in the other side of the world, a few hours away from here. I'm Ali. It's lovely to be with you today. So Matt spoke a lot about energy, and I want to take that into a few more concrete examples. But first of all, I want you to come on a journey with me a little bit and just think about how you feel when you look up into the sky in a warm summer night. You're looking up in the sky and you see a shooting star. What a wonder of nature, you probably think, like I do, and you stay watching in awe, waiting for another one. And you express a wish traditionally. And I want you to hold on to that thought. What is the wish you express when you see a shooting star in the sky? And given we're in the sky, let's stay there for a moment. And I want to ask you to imagine yourselves as astronauts in the vacuum of space, protected by a spaceship. How much different would life be? Well, we know that astronauts have been inhabiting the International Space Station, orbiting about 400 kilometers above Earth for over 24 years now. We know that they work, they wake up, they sleep, they eat, they go to the toilet, they do exercise, and they can even get their food delivered. While many of us might take advantage of this opportunity on Earth as well, we might see slightly different costs than they do. To get food to the International Space Station and any other item, especially consumables, the cost of delivery is remarkably higher than one would expect, going at a cheap rate of $10,000 per kilo, coming down from approximately 20 to 30,000 in the shuttle era. But it's not just the cost. And where does the cost come from? Well, the cost of growing 5 apples is the same as it is for the apples we buy on Earth, but there's energy that is required to get the food there. Not just that, the food needs to be prepared, sanitized, and made sure that it can last the journey to space. And I kid you not, sometimes the astronauts only get 2 apples because that's all NASA can afford. But if that's just 5 apples, what about water? What would you do? Would you ship water all the time like we buy milk at the supermarkets? Would you ship coffee or ship milk to the International Space Station? And of course, the answer is not. What they do on the International Space Station is take today's coffee, which gets processed by us, and turn it in tomorrow's coffee. Again, because water is one of the most precious and most expensive things one can get into space. What you see in here is a nicely named brine tank for the urine processing assembly in the International Space Station, where approximately 98% of the water is recovered. But that's only 98%, and that's just water. What about everything else? How do the astronauts handle rubbish? Well, this is a simple example of how astronauts handle rubbish. There is no place to put it. There is very little way to recover rubbish. And there is a lot of energy that this rubbish has required to be manufactured, sanitized, shipped up there. You think we'd invest a lot of money into making sure we can recover it. When we think rubbish, we're talking about human waste, but also logistics waste. And this is a lot of energy that is embodied in these 2 items. If we were on Earth, we would have recovery systems that can deal with part of them. But what we know, even on Earth, is that sometimes we just send things away. The rubbish truck comes and picks it up. If you have a sewage that gets taken care of automatically, if you have a septic tank, someone comes to pump it out for the solids every few years. What about the astronauts? I think you might have guessed correctly. This is what the astronauts do with the waste that they cannot recover. And so you spend $10,000 per kilo getting the materials up there. They get used once, maybe twice, if you think of wet wipes and cleaning materials or gloves for experiments. And maybe a couple of days later, they make their way into space as rubbish. I just want you to think that that doesn't just apply to the astronauts. This is a very specific example, and one that we care about because it's typically paid for with taxpayer dollars. We're not paying for NASA, but I can imagine that our colleagues in the US and colleagues in Europe and in Japan might be feeling somewhat guilty about spending dollars to get things up there that get used once and then are discarded. And when they're discarded, well, what happens? They come back down to Earth. I want to step back down to Earth now and just tell you a bit more about what we do. I work in the same institute as Matt does, and I am one of the chief investigators on an ARC research hub for future fibers, which is just a big research project that brings together industry, government, and higher education partners. We're a bunch of people, a bunch of researchers that do a lot of work to ensure that we can have a more sustainable future while not compromising on functionality of the materials we have. Matt just spoke to us about the importance of sustainable materials in terms of inputs and outputs as well. Sustainable processes, making sure that things last for a long time and the energy that is required to manufacture things is not too high. We want to ensure that if we make something that someone will need to use it, and if at the end of life, if they don't need to use it anymore, that someone else can use it. And in particular, we start from the end in this large research project. We start from the end, meaning that materials fate is what drives our work. Why? Because we plan for worst case scenario. We do know that we can only partly control the materials flows on the Earth. We know that for however hard we try, materials will be lost. I challenge each and every one of you to raise your hand if you have never lost something in the wind. But it's not just our own actions. Even if we put materials in landfill, we know that nature takes its course, and sometimes materials are not controlled. So if we take that perspective of the worst possible case scenario, what can we do to ensure that the materials that are traveling are not hurting the planet as much? We don't need to replace them as much. Well, first of all, we'd better reduce the number of materials we use, or the volumes of materials that we use, and ensure that we are nimble. The more the volume, the more the mass of materials that we use, the more the energy cost that is associated with them. Increase recyclability, and maybe try to ensure that if a plastic bottle ends up in the sea like this one, it becomes food, not harm for biology. And I'm going to focus on a particular type of materials that we all wear and we all often not look into very much. What we wear today, and most of us are wearing, is possibly looking a little bit different if you put it under a microscope than you think. We do a lot of textiles research in the ARC Research Hub for Future Fibers, and we focus on a couple of different aspects. We know that textiles are made with fibers, and we have a choice of the materials that we can make those fibers from. But we also have a choice on the coatings that are deposited on textiles to make them, for instance, rainproof. And we care about both of these aspects because what we know is that if we go and sample the water, that's exactly where we find our old textiles. And if you think you've never lost something, I challenge you to think again. What you see on the left-hand side of this screen is a microscope image of what lint coming from a washing machine looks like. Have you ever looked at it? It's a really good experiment to run with children. This is your old underwear. These are the fibers that are disappearing from your clothes when you're not watching. And to demonstrate that that happens, I took my own bathing suit that I used at the swimming pool a lot, and I discovered that it was old, and that by being old, it was simply losing material. What you see, these wriggly lines, wriggly bits that are whitish in the image in the middle, those are lycra fibers that have become degraded with time. And so if we look at what is happening when I'm swimming, I'm just shedding microfibers and microplastics everywhere. And materials go everywhere. The problem is they never go away enough for them not to be a problem for us. And what we're doing with our group is to engage with schools all over the world to help us understand where the materials are ending up in the environment. While that's materials fate, I want to bring you back to materials design. We have worked a lot with industry, and we have a couple of examples that we can show you as to how we go about designing materials for a better environment. We have a couple of examples here from industry partners that we have worked with, where the aim is to reduce the materials needs, reduce the energy needs, improve the comfort of the wearer, and reduce clothing weight. And this is a material that is made with recycled materials, like Matt was suggesting, in particular metals, and allows warm jacket to require half the amount of insulation than if we didn't have this coating. And to develop this material, we typically go through 3 key questions. We have a materials test. The material is worth investing in. Is the supply chain going to take up the materials that we suggest or design? And what about the next step? And if we took this particular example and if we apply the supply chain test, we can show you here an example from our partners taking recycled Nespresso containers, extracting the aluminium and depositing it on jackets to give great comfort to the wearers. And so we also showed you before a couple of images of fibers that go missing. Where do they go? Everywhere. But what can we do about that? If we can't really help textiles avoid shedding fibers, what can we do with that? Maybe it's time we start thinking about redesigning the gym shirts that we all wear. Most of us wear polyester and nylon shirts because they are more comfortable, they feel less wet than cotton t-shirts when we go to the gym. We all use Lycra. And this is exactly what the partners of the ARC Future Fibers Hub are doing together with us. We're working together to try to use regenerated cellulose as a substitute for polyester. We use other biopolymers, meaning materials that are derived from biology, but also we're trying to ensure that waste from other industries that otherwise might go burnt can find a path into textiles. And while you've all heard of bamboo fibers, for instance, I'm afraid I can share that most of those processes do not use sustainable solvents. This is where we're hoping that with the Future Fibers Hub, we can help replace those solvents with much greener solvents and much lower energy inputs required. And what then? We spoke about the first two tests. What about the third test? Well, this is where we are starting to set up real-life examples of degradability for textiles in a variety of environments, looking at how different textile processes affect the degradability of our textiles and how they affect the biology around them. But then what? What if you understand what happens to the materials, and what if you develop a material that is highly degradable? So I want to bring you back to space and back to the gym into space and back to smelly clothes and clothes you can't ditch, if not every 6 months. So clothes that you probably want to ensure have another function. So in our ideal world, we will be able to go to the gym as astronauts, put the clothes into the veggie patch, grow some nice rocket or lettuce, eat it, then through some processing, ensure it can go back to this. It's easy to think about astronauts as a special case. They're in their own little spaceship with their own little atmosphere, so fragile, so precious, and we fear that they are in vacuum of space. But that's no different to us. We are on a slightly larger spaceship, but the atmosphere we have is still very thin, very fragile. And the thought that investing in materials research, lowering the energy cost that goes into production of materials, and our daily life, lowering our footprint, might play a big role in ensuring that this thin atmosphere, which is described as just a sliver over the horizon, can stay as unpolluted as possible. And if we step back a little bit more, we go to the next close to habitable planet. Well, that's as big as Earth is. That is a long way. And I challenge you to tell me that there's a point in thinking that we can one day move to Mars, especially if we can't look after Earth in the first place. So that's how we envisage materials research, something that helps us live a great life, but also something that helps the new generations live a good life. Regenerate the environment is what we want to do, but it does take a lot of thought into all the various aspects: materials selection, supply chain considerations, and, actual test. What happens to the materials after we make them? So I'm just going to close with one last question, which is, when you next look up to the sky and you see a shooting star, what is your next wish? Thank you.